point, let me know. All right, let's look at another way of looking at dimensionality reduction. See, what we did so far in PCA or SVD is that we try to transform data or approximate data by doing some kind of matrix factorization. Another way is, if I have 13 features and I want to get 5 features, maybe I can discard 8 features and just keep 5 features. All right. Question is, how do I know which particular combination of 5 features is to be kept and what are those 8 features that should be discarded? All right. So in the PCA, we are transforming the features to do the reduction. In this method, we do not do any transformation. We just try to figure out what is the best subset of features that can be used in place of all the features. All right. So this is known as dimensionality reduction via feature subset selection. So the idea here is to select a subset of k features out of n original features. All right. Obviously, if you have n original features and you want to pick k, there are a number of ways in which you can do that. And the number of possible ways in this particular case is factorial n divided by factorial k times factorial n minus k. All right. So if you take n equal to 20 and k equal to 5 and plug in the numbers, you find that the number of possible subsets is 15,504. That means so many different possibilities are there. And what we need to do is to pick one possibility out of those possibilities, which is the best possibility. All right. That means we need to do some kind of search. We need to go over these combinations and figure out which is the best combination. All right. Now, when the number of possibilities is small, then one can do what we call as an exhaustive search. That is, you can go over every possibility one by one and see how good is that. But for an example like this or any other similar example, the number of possibilities is going to be very large. So exhaustive search may not be a good idea to proceed. So what you want to do is you want to have some kind of trick that tells you which particular combination is really a good combination. All right. So what one can do is one can kind of think of an approach like this. So you start at the bottom left with the attributes, and you have some method, let's call it as a search strategy, which picks k attributes or defines what is the subset you want to pick. So you pick the subset, and then you need to have some kind of method that tells you how good is that subset. So you have an evaluation criteria. All right. And as you go over different possible subsets, at some point you need to stop. Otherwise, you will keep on going through your search process. All right. So you define some kind of stopping criteria. And once you hit that, you can say that you have selected your subset. All right. So this is an approach which we call as the feature subset selection approach or feature subset selection process. So there are two components, important components in this process. Number one, a way to figure out how to pick a subset. And number two, how to do an evaluation of a given subset. How to figure out whether a given subset is really good or not. All right. So what we need to do is we need to have some kind of measure which tells us whether a subset is good or not. And suppose we are doing this subset selection to build classification models. In that case, what we can do is we can use a evaluation metric that will tell us whether this subset is good for classification model or not. And if it is good, we will keep it. If it is not good, we'll discard it. All right. So there are two possible measures. One could create their own new measures, but we will discuss only two of them here. One is known as the divergence, and the other one is known as scatter matrices based measures. All right. So we will look at these two measures now. And the idea of divergence is related to the idea of entropy, which I think I mentioned in one of the earlier lectures, but let us take a look at it again. So entropy is a measure of uncertainty. A system with no uncertainty has zero entropy. And if a system has a lot of uncertainty, then its entropy value is very high. All right. So to define how we measure entropy, let us consider a situation where there are n possible outcomes of an event. So there is some phenomena that takes place, and there are n possibilities that could occur as a result of that phenomenon, or n possible outcomes. And let P sub I indicate the probability that the outcome is going to be the ith outcome. All right. So every outcome has a different probability. In that case, we can say, all right, the entropy of this phenomena or event is given by minus sum of I equal to 1 to n pi log pi. Or you can write it also as summation pi log 1 upon pi, if you don't want to carry the negatives. All right. So this is the definition of entropy. And the divergence idea is based on this definition. But before we go that, again, let's look at one more slide on entropy. So the entropy H is 0 if and only if exactly one event has a possibility of 1. That is, if the phenomena has only one outcome, then entropy is 0. All right. Entropy H has a maximum value if all possible outcomes have equal probability. So if you have n possible outcomes and each and every outcome has an equal probability, then entropy maximum. For example, if you have a coin and the coin is not manipulated or biased, obviously when you toss the coin, either it can be head or tail. All right. Both have equal probability. So you can say the entropy of tossing a coin and observing a head or tail, that entropy is maximum equal to 1. All right. And of course, if you look at two events, event X and event Y, then the joint entropy of two events is less than or equal to the sum of individual entropies. All right. So those are some of the things you need to remember. Let's look at what we mean by divergence, which is also known as what we call as cross entropy. So suppose we are given two discrete probability distributions. Then KL divergence, which stands for Kullback and liberal divergence, it measures the similarity of these two probability distributions. All right. Now, instead of saying two probability distributions, let us say we have two different events. Event number one has certain possibilities, and each possibility has a corresponding probability. Event number two has certain possibilities and has corresponding probability. All right. And let's say both events have 5 possible outcomes, but the corresponding probabilities are different. All right. Then one might say, well, how similar are these two events? Okay. That is what basically we are trying to measure here in terms of two discrete probability distributions. All right. So KL divergence measures that. So KL divergence says, all right, the divergence between P and Q, or given Q, divergence for P is given by this expression Pi log Pi divided by Qi. All right. This is also known as I said, is cross entropy. All right. You can see that this is a non-negative and zero if and only if Pi is equal to Qi for all I values. All right. Otherwise, it's not equal to 0. All right. Other thing is the way we have defined it, you can see that if I interchange Q and P on the left-hand side, then obviously the formula on the right-hand side will change. All right. Then you will have to switch between P and Q on the right-hand side also. All right. That means this measure is not a symmetric measure. That is, when you measure from P to Q or Q to P, you will end up with different results. All right. Typically, what we want P to Q or Q to P should give us similar outcome. So what one can do is one can take P to Q and Q to P formulas and add them up. That way, it doesn't matter whether you measure from P to Q or Q to P, you will end up with the same result. All right. So that is how we define Kullback and Leibler divergence. This is the formula for that in the case of discrete probabilities. Here is an example. So let's say that we have two phenomena. Both of them have 3 possible outcomes, 0, 1, and 2. The probabilities for these outcomes are different in the two phenomena. The first one is 0.36, 0.48, and 0.16. In the second case, 0.333, 0.333, 0.333. All right. So we can now calculate what is the divergence. All right. And so P to Q and Q to P can be calculated as I shown you in the calculations. And if you want a symmetric result, then all you need to do is to add them up and divide by 2 if you want. All right. So that's how this divergence is measured. All right. In many cases, we are dealing with normal or Gaussian distributions. So in such cases, one can derive in the closed form a formula for measuring this divergence. So given two Gaussian or normal distributions with corresponding means as M1 and M2 and corresponding covariance matrices as C1 and C2, the formula for divergence is as shown. All right. And I think there is an example here shown. So if I have mean vector 3, 3, second mean vector 2.3, 2.3, covariance matrix is diagonal with 0.2 in the first case and diagonal with 1.9 in the second case. What is the value of DKL? We can calculate it, or we can go to our libraries in Python and do the calculation. So basically the calculation is shown here. Basically all I have done is I have plugged in that formula and calculated the result. All right, so that's how one can calculate the divergence. All right, let us see where we are. Okay. Another measure to check how good is a particular subset of features is through what we call as a scatter matrices based measure. All right. So there is a concept of class scatter matrix, which is pretty similar to a covariance matrix, except that in a covariance matrix, you have a division 1 by n minus 1, which is not here, all right? So class scatter matrix S of J is for all the examples that you have from the jth category or jth label, all right? So that matrix is defined as shown. And if you have only two classes, then for J1 and J2, you can define the respective formulas, all right? And then one can also define what we call as a within class scatter matrix, which is nothing but sum of two individual scatter matrices. One can also define between class scatter matrix, which is basically a measure of how far the two mean vectors are from each other. So you can see that SB is simply measuring, in some sense, how far the mean vectors are, all right? And one can also define what we call as a mixture scatter matrix, which is a sum of SW and SB. These three matrices are pretty useful in number of things, and they are also used in evaluating different features. And the way these matrices are used for evaluating different features is based on some of the properties of these matrices. So there is a measure called J1, which is defined as the trace of matrix SM divided by trace of matrix SW. Remember, trace of a matrix is nothing but the sum of diagonal elements. So basically, you do that, or J2, which is the trace of SM divided, determinant of matrix SM divided by determinant of matrix SW, or another criteria J3, which is nothing but trace of matrix SW inverse multiplied with SM. These measures take on high values when data from two classes are far away, can be separated easily. If they don't take high values, it means there is a lot of overlap in the data from two classes. So one can look at these numbers and get an idea whether a given subset of features is likely to give you good results or not. All right. So we will stop at this point. And what we will do is we will in the next class look at, okay, we have taken care of how to evaluate. Now question is, how do we figure out subsets that we should be evaluating? Is there some kind of strategy that we can use? So that is what we will work on in the next lecture, and whatever else is left under dimensionality reduction and visualization. All right, so we'll stop here. Thank you.
Professor?
Now, in the method we just described, what we did is we started with all the features and we eliminated one feature at a time. One can follow a slightly opposite approach. You could start with one feature at a time and keep on adding additional features till you come to a stage where you have the desired number of features. All right. So this will be known as sequential forward selection strategy. So here we start with a single feature. So we'll do the evaluation using single feature. And let us say we find the X1 is the best feature. Then what we will do is we will form all combinations of two features at a time. So X1, X2, X2, X1, X3, X1, X4, and then do the evaluation and pick the best combination. And if we want to proceed further, we will follow the same procedure and proceed further. All right. So these two strategies, sequential backward and sequential forward strategies, are pretty similar in concept. In one case, you start with all the features. In another case, you start with a single feature. But you have a way of figuring out how to look for the best combination. And again, this procedure is going to give you suboptimal result. And the number of operations that you are going to need in this particular case is given by this formula. All right. So subset selection method is one way of reducing the features. There is another technique which is quite popular and people have used it in many cases. This is known as genetic algorithms for feature reduction. Genetic algorithms are basically algorithms that allow you to do search without worrying about derivatives or gradients. So that's why these methods or techniques based on genetic algorithms are known as derivative-free search methods. The basic idea behind genetic algorithms is based on the idea of natural selection and evolution. So these are biologically motivated algorithms. And these algorithms can run in parallel. That means if one can do a brute force search, which is what these algorithms perform, but that search can be carried out in parallel on number of parallel processing machines. And these algorithms can be applied to discrete and continuous optimization problems. And these methods are less prone to what we call as a locally minimum solutions. Many times when you are trying to minimize a criterion function, the criterion function might have several minimas. One of them could be the best of the best minima, which you can call as a global minima. And there might be several other minimas. So generally, there are algorithms which basically make use of derivatives. Those algorithms have a tendency to get stuck in a local minima. Genetic algorithms are not prone to that tendency, and they can give you the solution which is globally minimum solution or best of the best solution. All right. The approach using genetic algorithms to solve any problem, including the problem of doing feature reduction. This is a pretty general approach. You can apply it to any particular problem that you might be working with. So what are the steps or what is the general problem solving approach using genetic algorithms? Number one, you need to come up with a bit string representation for your solution space. That is, solution has to be represented in the form of a string of bits, zeros, and ones. And typically, the term that people use in genetic algorithms for that is chromosomes. Then you need to define a fitness function, which is very similar to the evaluation metric concept we talked earlier. And then you form an initial gene pool, which is the initial population of your solutions. And then this population is allowed to evolve through successive generations. And every new generation is supposed to give you a better solution for your problem. So if you go through many, many generations, you ultimately end up with a solution that is your desired optimal solution. All right. So this is generally the basic framework for problem solving using genetic algorithm for any application. And same can be applied here. All right. So one thing that requires a little more explanation on this slide is evolve using genetic operators. So basic idea is that you create a bit vector that represents a potential solution, and you initialize a large number of such bit vectors with different ones and zeros. So basically, you are initializing a large number of potential solutions. And then a pair of these solutions, pairwise, these solutions interact with each other, just like a male and a female interacting with each other, and they create new potential solutions. And these new potential solutions are created using genetic operators. So basically, all you have to do is to define how to represent the solution and define a set of genetic operators and apply them to your problem. So what are the some of the examples of genetic operators? These genetic operators could be characterized as single point crossover. So if you look at the top, basically what we are showing is that two pairs of chromosomes on the left-hand side come in contact with each other. And at some point, which is the dotted line shown here, they switch the last few bits of their chromosome. So you can see that you have on the left-hand side two patterns, and on the right-hand side, you have two patterns which are result of single point crossover. All right. Same idea can be applied using what we call as a double point crossover. So you define now 2 points where crossover can take place. The another one is mutation. You could apply the idea of mutation, and in the case of mutation, a 0 or 1 on the input side will flip and give rise to a complementary value or inverted value. All right. So like this, one can define few different operators, and these can be applied in a random fashion on your population to create new population. And when you create new population, you basically apply the fitness function and keep those members of the new population who are above certain fitness value that you observed in the previous population, and rest of them are discarded, and the process keeps on repeating. So basically, every new generation gives you a solution or a set of potential solutions which are better than the set of potential solutions you had in the prior generation. And if this process is continued for a long time, obviously you end up with a really good solution. So that's the basic concept of applying genetic algorithms in this particular case, as well as in general into any particular problem. So basically, one can represent the process of genetic algorithms, including evolution, through this diagram, which basically shows how you select two pairs of potential solutions and then how they get modified through many of those genetic operations that you define. And then you look at the resulting population and check their suitability, or run them through your metric of fitness function, and keep the ones that are deemed very fit and discard rest of them and repeat the process. All right. So people have followed this approach, and they have worked with this method to show that this method can generate pretty good results for dimensionality reduction. And what this chart is showing, or what this table is showing, is something like this. That is, if you look at the UCI Irvine repository for machine learning data sets, you will find that at that location, there are large number of data sets that people have been using for last 20, 30 years. So for those data sets, the results are well known. So what one can do is one can take many of those data sets and apply your algorithm and compare the results that you get with the best known results that are out there, and show that, well, your algorithm does really a very good job. So that is what this table is showing. They have taken a large number of data sets from that site, and for each and every data set, they have gone through this process of feature selection using genetic algorithms, and then they have built the classifiers, and then they are showing that, okay, through this approach, this is the result we get, and through the other approaches or whatever is out in the literature, those are the results. And one can compare and see that this approach does give you good performance. All right. So that's another way of doing feature selection or dimensionality reduction. So one can write down this in the form of a flow chart to see how this whole process can be applied. All right. So it's basically what I showed you in the previous slides, just represented in the form of a flow chart. All right. Now let's look at one situation or one type of situations where the methods that we have discussed so far do not really work. Why? Because the methods we have discussed so far are methods that you can call as linear methods. They are good for distributions that you can call, or you can characterize as linear distribution. All right. Let's take a look at this picture here. And if you look at the data set that is shown in the left-hand side, basically it's a kind of a, think of a roll, flexible roll that you can fold or you can roll it. And on that roll, you have points coming from different classes. So the blue points represent data coming from blue class, the yellow points represent data coming from yellow class, and so on and so forth. All right. So if you look at this data here, the data is distributed in 3 dimensions. All right. You have X, Y, and Z. Every point is characterized by 3 coordinates. All right. But inherently, this data is nonlinear. And if you were to apply PCA or any other kind of technique, the mapping that you will get is going to look something like what is shown on the right-hand side. But the important point here is that if you look at a point on the left-hand side in the original data space, although the data is in 3 dimensions, but every point has a local neighborhood which is in 2 dimensions. So what one can do is one can characterize this data set by relying upon the idea that the points in the local neighborhood are close to each other, while the points that are not in the local neighborhood are are different from the local neighborhood points lying on the road. So what you can do is you can actually make use of some kind of nonlinear projection, which will unroll the data in such a way that it takes into account the local neighborhood relationships, such that when you do that projection, you end up with a result that is shown on the right-hand side. And you can see that this right-hand side result looks much better than what we saw in the earlier slide. So basically what one can do is, for situations where the data is lying in many folds, we can make use of a nonlinear technique. And there are a number of nonlinear techniques to do the dimensionality reduction or to do the visualization. What we are going to do is we are going to look at only one nonlinear technique, which is very popular nowadays. And this technique is known as a t-SNE method. So we are going to be describing this method in the next slide and so on. So what is t-SNE method? So let's look at first SNE. What does it stand for? SNE stands for stochastic neighborhood embedding. So there was a method that was proposed earlier, which was called SNE, or stochastic neighborhood embedding method, to generate nonlinear projections. It turned out that that method had certain deficiencies, and a modification of that method was made. And that modification is known as t-SNE method, where T stands for students T distribution. Now, you're all familiar with Gaussian distribution, but there is another related distribution, which is known as students T distribution. So in the original SNE method, people were using Gaussian method. And because of that, there were certain issues that were resulting in not very good results. By replacing the Gaussian with the student T distribution, the deficiencies of the method were removed, and the method became very popular and it's very useful. So let's look at what this method is. So let us say that we have capital N data points in a high dimensional space, as we have assumed earlier also for PCA, etc., etc. Let's pick any pair of points xi and xj, and let us say that Pij represents the similarity between these 2 points. One can define this similarity in a number of ways. So let us define the similarity of j to I. So that will be represented as Pj given I, or Pj with respect to I. And we define that similarity through the expression that you see here, e to the power minus something divided by sum of all the e to the powers over all the indices. All right. So if you look at this expression really is defining the probability that ith point would pick the jth point as its neighbor if neighbors were picked in proportion to their probability density under a Gaussian centered at the ith point. So you can assume that at ith point we put a Gaussian, and then we look at where is the point j sitting on that Gaussian, and we calculate the probability there and normalize that with all the points that we have in our distribution. So that gives you probability P of j given I. And since this formula is not, that is, since we want a symmetrical formula to measure the similarity between I and j, or j or I, so what we can do is we can define Pij as sum of P of j given I plus P of I given j divided by 2n, and that becomes a symmetric measure for similarity. All right. So this is what one can do. And you can see that there is a parameter here called sigma I, which is actually known as a perplexity parameter, and it can be used to adjust how large the neighborhood is to be considered. So let's use these formulas to measure the similarity between 2 points in a high dimensional space. Now, the idea here is that take this collection of points in the high dimensional space and somehow or other project them into a lower dimensional space. And lower dimensional space could be 2-dimensional or 3-dimensional. Typically, that's what people choose, 2 or 3-dimensional. All right. So when you want to map these points from high dimensional space to lower dimensional space, obviously there is going to be approximation involved. All right. So the basic idea is that if there is a pair of points that is close to each other in the high dimensional space, when you map them into lower dimensional space, you want that pair of points again to be close to each other. And you need to maintain this condition over all potential pairs that you have. All right. So let's assume that somehow or other we have done the mapping, and let us define now the similarity of point I and point J in the lower dimensional space after mapping. So that similarity let us define as Qij, and that is defined through the formula that is shown here. So this is the formula that is being used in the 2-dimensional space to define the similarity. Now, in the high dimensional space, remember, we were calculating the similarity using Gaussian distribution. In this case, original method used the Gaussian distribution, but in the t-SNE method, the distribution that is being used is known as the student's t-distribution, with a single degree of freedom to calculate the similarities. And the formula for student t-distribution is shown there, f of z equal to 1 divided by 1 plus z squared. All right. So let's see why this was used and what is the difference between the student t-distribution and the Gaussian distribution. So you can see here there are 2 curves I'm showing you. Both are bell-shaped curves. All right. If you look at the blue curve, that is your familiar Gaussian distribution. All right. If you look at the orange curve, that is known as the student t-distribution. The big difference between the two is that the student t-distribution has heavier tails. That is, as you go away from center and move towards the tail end of the curve on both sides, all right, the student t-distribution still has some value, while Gaussian distribution is almost close to nil value. All right. So that is the difference between the two. And this difference is what makes this method, t-SNE method, more useful compared to the original SNE method. Again, let us see why they ended up using this. So let's see what will happen. So let us say that we generate uniformly distributed random points within a sphere of increasing dimensions, but same radius. That is, suppose you start writing code to generate random points within a sphere of certain fixed size. All right. And what you do is a sphere of fixed radius. What you do is you do this for 1 dimension, 2 dimensions, 3 dimensions, so on and so forth. All right. So you keep doing. And once you've done this for several dimensions, let's calculate the histogram of distances of the generated points from the origin. So let's measure how far the points are lying from origin in these different high dimensional spaces when the points are uniformly distributed. All right. So if you look at the 3 histograms that we are showing, we are getting for d equal to 2, d equal to 5, d equal to 10. All right. It turns out that if we were to look at the histograms for our problems in the high dimensional space and lower dimensional space after mapping or before mapping and did the histogramming, it turns out that using student T gives us a better matching with the resulting histograms. That means whatever results under the assumption that the data is having student T distribution, we get the histograms. Those histograms match well with the method that we are using to map the points from high dimensional space to low dimensional space. So that's why student T distribution is used in this stochastic neighborhood embedding method, and the resulting method is called t-SNE method. All right. So now the question is, how do we get the mapping? So we know how to measure the similarity and why we want to use student T distribution. But the question is, how do we actually get the mapping done? So mapping is done by defining a criterion function and then optimizing that criterion function using a search technique. All right. So basically, you can say that the points in the original high dimensional space are fixed because those are given. Mapping in the lower dimensional space is where we can move them a little bit around and get the better results. All right. So we can do that by minimizing the criteria that is shown here. And if you look at this criterion, this is what we mentioned also in the last class, Kullback-Leibler divergence that we define. All right. So that is the metric or the measurement that, or the criterion that we use here to minimize this criterion and get our best mapping. All right. Now to minimize it, what we need to do is we need to perform some kind of optimization technique. In this particular case, we can use what we call as a gradient descent. That is, we take the partial derivative with respect to the mapping positions or mapping points and see what value we get for the partial derivative. So that's our gradient, and then use that value to basically improve our solution. So basically, it is a gradient search-based technique, and we will talk a little more about gradient search later on. All right. So for the time being, it's just sufficient to say that we follow a gradient search strategy to get the solution. So here is an example. So what we are showing you here is a selection of 64-dimensional digits. So we have digits in the form of 8 by 8 matrix. So each digit is of size 8 by 8. So each digit you can say is a 64-dimensional vector. All right. And we have a collection of such digits. In this particular case, the number is 1797. So we have so many points in a high dimensional space, which is a 64-dimensional space. What we want to do is we want to map these points from a 64-dimensional space to a 2-dimensional space. And we want to do that mapping by using t-SNE method. All right. And remember, this method is a search technique, gradient search method. All right. So you can see here what has happened is, or what is happening is that gradient search starts with some initial solution, which is the beginning of this movie. And as the search goes on, we move towards the solution. And what is it that you can observe here? You can see that all the digits that represent 7 are all grouped together. Digits representing 6 are all grouped together. Digits representing 0 are all grouped together. That means from high dimensional space, where all the zeros would be close to each other, all the 6s will be close to each other because they have similar patterns. All right. When we map them, we are able to maintain that neighborhood for those points in the lower dimensional space. At the same time, we are able to move digits representing different numbers away from each other so that each collection of points representing a particular digit is lying together more or less. All right. So this is what t-SNE method can do for you. So in this case, what you can see here is, sorry, let's go back. If the end result after mapping in the lower dimensional space is such that objects or points from different classes or with different labels are lying away from each other, they're well separated. That means the problem that you have at hand is a relatively easy problem to solve. If by mapping in 2 dimensions, the points were overlapping from different classes, they were heavily overlapping, that means those points also highly overlap in the high dimensions. That means you are looking at a problem that is going to be difficult to model or difficult to solve. So again, by visualization like this, you can get a good idea of the complexity of the problem as well as some overlapping, etc., that might be present. All right. Any question, anything? All right, so how do we use this? I just showed you the example. So remember, it's a gradient search algorithm. One thing about gradient search algorithms is that to initiate the search, you have to define some kind of initial solution. And then the search proceeds from that initial solution, number one. Number two, gradient search techniques are susceptible to local minima. So if you define an initial solution which is sitting close to a local minimum, then as soon as your search begins, your solution will come from the local minimum. On the other hand, if you initialize your solution or search at some other point where there is no close by local minima, then chances are that your search will proceed nicely and it will end up at the global minima. And if there are multiple local minimas, then depending upon where you start, you might end up with a different result. So the point is that it's a gradient search technique. You can end up with slightly different results every time you search with a different initial solution. So typically what people do is that to minimize this and to make the search more consistent, what you do is you always choose your initial solution as a mapping that you will get using PCA into 2 dimensions. So that becomes your good starting point. And it is the same starting point as long as you apply PCA and reduce the data to 2 dimensions. So with that, then you don't have any hassle of ending up with a different solution every time you run this algorithm. All right. Other point relates to the demo. In the demo, I colored digits with different colors, all right? That does not mean that this method, t-SNE method, makes use of class labels. The method does not rely on class labels, all right? Those labels were put in just to illustrate the idea that digits from different classes get nicely separated by t-SNE method. t-SNE method does not take into account any class labels, all right? And the perplexity parameter, the way the algorithm is implemented in sklearn library, it is automatically determined. However, if you want, you can specify this parameter on your own. But the sklearn library has a built-in way of calculating this parameter based on the density of the points that you have in the high dimensional space, and use that to figure out what will be the best perplexity parameter. All right. So with that, okay, here is another example of t-SNE applied to the wine data. Again, you remember we have talked about the wine data. So if you apply t-SNE to wine data, this is what you end up in 2 dimensions. All right. So you can see here the 3 classes are nicely separated, except that there are 2 twos sitting below the group of ones. All right. That means those 2 examples are very likely to be misclassified. And similarly, there might be 1 or 2 twos close to 3s that might get misclassified. So you can say that this wine data will be easily separable, and you will be able to achieve a decent accuracy somewhere around 90, 95, 96% in terms of building a classification model, because the points are nicely separated except very few points. All right. So again, you can use this method to get an idea of how complex your problem is. And that shows you the PCA mapping of wine data with 2, so you can compare that. So let's summarize the dimensionality reduction things that we have discussed. So as we have seen, there are many methods for feature selection and dimensionality reduction. We have looked some of them. And among the methods that we have looked at, PCA or eigenvector or KL transform, that these are all the names for the same thing. It's a popular approach to obtain low dimensional space via linear projection. t-SNE approach is currently in favor for linear as well as for nonlinear configurations. Other methods or approaches that are possible are known as isomap, kernel PCA, MDS, multidimensional scaling, LDA, linear discriminant analysis, MLDA, multiple linear discriminant analysis. Out of these, we will be talking about MDS and LDA, MLDA later on. All right. So you can say that, all right, there are a number of methods that are out there, and we have looked at some of them, and we are likely to look at some more of them later on in this particular course. All right. So with that, I think our discussion on this particular topic is over. Okay. So let me go back and pull out something different so that we can keep on discussing. We can have a few minutes break in between before I set it. So if somebody wants to go out, you can go out and come back in 5 minutes or so. Okay.